Good evening, everyone. Welcome to the 15th talk of this year's CASILab Saturday Lecture Series. CASILab, the Center for Advanced Studies and Innovation Laboratory, is committed to demonstration-based science education, research, and innovation. It serves as a platform for institutional, independent, and grassroots researchers to engage in cutting-edge projects. Today's lecture is particularly special to me. Our distinguished speaker, Dr. Tushar De, is one of the founding fathers of CASILab, established in 2018. He is also one of my direct teachers. Professor De completed his master's and PhD in physics from Bardhaman University and later joined as an assistant professor at Gurucharan College, Silchar, where he served his whole career, retiring as an associate professor in 2018. Remarkably, he was among the earliest to clear the national test for lecturership. I think that's what it is to be called, is the predecessor of today's NET exam during the late 1970s. His research spans a wide spectrum from gravitational lensing by wormholes, early universe cosmology, to atom field entanglement and quantum information theory, especially involving quadrate systems. But he is, as far as I know, a core general theorist, as far as I know. But he, of course, is also now a very involved physicist in quantum optics and quantum information theory. I'd especially like to mention his highly influential paper, The Gravitational Lensing by Wormholes, co-authored with Dr. Suraj Chen, who is also with us today. This paper has been cited over 117 times. In this work, they explored how wormholes could influence light bending, and this paper has become a cornerstone reference in the field of gravitational lensing and exotic space-time structures. Today's lecture is dedicated to the International Year of Quantum Science and Technology. I'm pleased and honored to introduce today's speaker, Professor Tushar De, who will speak on entangled quadrates and inequalities in SU3 basis. Please join me in giving a very warm and heartfelt welcome to Professor De.
Thank you. So today I shall give a lecture on entangled quadrates and inequalities in SU3 basis. First, I just give an outline of my talk, and I shall give a introduction with qubit, and also I shall introduce the term quantum entanglement and build CHS's inequality, because these things are in our work. I have take help of the inequalities and entanglement property. And next, we shall talk about SU2 group and Bell states, how the Bell states are constructed by the use of SU2 group. Then we shall discuss about correlation tensor and Bell inequality. And this Bell inequality is the turning point of quantum mechanics, which introduced the term entanglement. And next we shall go to the SU3 group and QT states, and we shall construct QT states with the help of SU3 group representation. And next we shall discuss about the correlation tensor in SU3 and QT inequality, and we shall discuss about the inequality we have found in QT system. And next, the conclusion. Our work. This lecture is based on our work and inequality of our entangled quadrates in SU3 basis, and it is published in Quantum Information Processing in the year 2024. So I shall start with the terminology qubit. We know that in quantum information, I know that in information processing, as in the classical physics, in modern day quantum, modern day computer, is the bit, and bit is represented by two states, 0 and 1. It is in the classical bit, and it is it depends 0 and 1. And in analogy with this classical system, in the case of quantum information or quantum computing, we call it as quantum qubit. Qubit is the short form of quantum bit, and it is also represented by two states, and it is 0 and 1, like in the classical case also. Classical bit, it is 0 and 1. Here also it is also 0 and 1, and it is represented by ket 0 and ket 1. And also you know that a qubit can also be in a superposition state, like psi equal to alpha 0 plus beta 1. So it is not, as in the classical case, it is only 0 and 1, but in the quantum case, the qubit can also be in a state, it is all superposition state. It is the summation, it is a linear sum of 0 and 1 state with some coefficient alpha and beta, and the condition in this case, the condition should be satisfied by this alpha beta r, alpha square beta square should be 1. This condition should be satisfied. It is the normalization condition, and this quantum bit can also be represented by a geometrically can represented this quantum bit, and it is just the block sphere. This is the classical case 0 and 1, and in the quantum case, you can represent this superposition, this qubit by a block sphere. It is called, this sphere is called block sphere. It is a unit sphere, and 0 is the north pole, is the 0 state, and the south pole is the state 1. And any other point on this sphere, in this unit sphere, is a superposition state. So you can say that a qubit can have or this superposition state can have any possible state, innumerable states, depending on the values of alpha and beta. You can take many combinations of alpha and beta to get points on this surface. So this superposition allows this these states, all these states. So next we shall discuss about the entanglement, quantum entanglement. It is a concept of quantum mechanics only. There is no classical analog of this quantum entanglement. So the basic definition is, it is the, if you have two systems by a bipartite system, there is no, there is, if there is any correlation, and this correlation is non-classical correlation between quantum particles. So these particles are correlated in non-classical way. That means, what does it mean? It means if two particles interact initially, but now they are separated, and if you can find, if you make a measurement on one particle, you can say the value of the other particle also. It is determined. The value, the measurement on first particle will determine the value of the second particle also. This is a kind of, this is called entanglement, quantum entanglement. And these two particles, those are particles are specially separated. Measurement on one particle fix the value of the other particle also. So for a bipartite system, you have this Bell states. It is the two qubit states, and there are four Bell states: phi plus, phi minus, psi plus, psi minus. These are the four Bell states, and they are entangled states. Now, I shall give a mathematical definition of this entangled states. Suppose this H1 or H2 are two finite dimensional Hilbert and if psi belongs to the product state of H1 and H2, so that psi1 belongs to H1 and psi2 belongs to H2, then psi is said to be separable or product state if you can write this way. If the final state psi is written as a product of psi1 and psi2, we call the state psi is separable. If you cannot write this way, you call this state to be entangled states. That is the definition of entangled states. For example, you take an example, this 1, 1, 1, 1, half of 1 on 1. This is a state. If you see that you can write this state to be as the product of two states, 1 upon square root to 1, 1 and tensor product of 1 upon root to 1, 1. So in this case, you see that you can write in this form, psi1 cross psi2. So this is not a, this state is not an entangled state, it is a product state. So this is the example of product state, but if you take the Bell state, therefore these four Bell states you cannot write as the product states. You cannot write these four Bell states as the product states, so the Bell states are entangled states. So next, we shall, in order to, we shall discuss about the Bell CHHS inequality, because this Bell inequality is the test whether entanglement exists or not. So we shall discuss this part. This thought experiment is due to there is a objection of the completeness of the quantum mechanics. It is Einstein. There is a famous paper, Einstein, Rosen, and Podolsky. They tried to show that Bell's quantum mechanics is not complete. So, in order to disprove the idea of Einstein, Bell suggests an experiment, thought experiment, to disprove the idea of Einstein. So we shall discuss this experiment here, and it is actually not the Bell experiment in that sense. It is Bell series inequality. So here, Bell actually take the for the time being we think that we are not talking about quantum mechanics. It is only in the domain of classical physics. We try to do an experiment and check what is the result of this experiment. Then we shall suppose Charlie prepare two particles and send one particle to Alice and another particle to Bob. So I repeat, Charlie prepare two particles and he send one particle to Alice and the other particle to Bob. And after getting the particle Alice can do some experiment on his particle to get some physical property, and we call that, and suppose there are two physical properties he measured, and Alice measured this Q and R, and we call this physical property as PQ and PR. And also the measurement value of this measurement is Q and value and R. Also, you assume that the values of Q and R is to be plus minus 1. Q has the value plus minus 1 or R has the value plus minus 1 for simplicity.